All right. Good morning, everybody. So I'm a little bit late today because, well, not exactly late because it's still we still got about 2 minutes to go. But I had a different meeting. I got double booked for a faculty meeting, which is kind of interesting because, as it turns out, from our VP of instruction at ARC, I just learned that we're going to have a drop of, well, there's a request from the district to reduce our class offering by 12% in the fall. So that's largely because of a budget issue. And that budget issue is not going to go away anytime soon. I listened to a webinar, that talked about the governor's the budget for basically the next year or two, and things are not looking up in terms of how much money we are going to get to operate basically all the community colleges. So we're going to see some major cuts in terms of classes being offered and stuff like that. And the other meeting, which is still ongoing right now, they're basically talking about how do we set the priority on what classes get canceled and what classes get to go, how many units, or how many classes we offer, for this, how many classes we offer for that, and so on. So it's kind of, disturbing things, disturbing topics, but at the same time, kind of important topics, for the administrators and the faculty to talk about, things. All right. Yeah, I know, Alex. It kind of sucks, for a lot of people. The first people, or there are many people who will get impacted by this. Students, obviously, like you, are going to be impacted because you can no longer get the classes that you need to get to. So graduation dates, and stuff like that, it's going to be stretched out. And then the part-time faculty will also be impacted quite a bit, because when we cut classes, it is the part-time faculty who will basically have their classes cut first. So the bottom line is, those people who teach, we call those adjunct faculty. Those professors as part-time professors. So they will probably see a major, some of them anyway, will see a major reduction in terms of how many classes they can teach, which directly link to their income. So it's gonna be bad for a lot of people, and we're trying to figure out how to minimize the impact. But no matter what we do, there will be some impact. All right, so let me just take a quick look at the time. It is, oh, okay, we are already 1 minute past, so I'm gonna get started. So what we'll do today is to talk about injection, surjection, and bijection. All of those are qualifications over functions. In other words, an injection is a function, but it has special properties. A surjection is also a function, but it also has special properties. When a function has properties that qualifies it as an injection and a surjection, then it becomes a bijection. So, well, I'm done with that whole module already. We can now move on, right? Well, not quite, right? Because I have to go in and really talk about what qualifies a function as an injection and so on. So what we'll do is we are opening up this module and take a look at this module. All right. So out of this module, the first thing we talk about is injection. So at this point, I'm really hoping that everybody has a nice long weekend. It was a little bit hot. Okay, it's starting to cool down now, but we also have fires going on, lots of smoke, and stuff like that. But nonetheless, I hope you guys have a restful weekend. But I also hope that most people have some time to review the material to basically remember what a function is. Because what an injection is it is basically a function to begin with. In other words, an injection is a function. But in addition to being a function, it also meets a particular requirement. So in just plain English, okay, this is what it means. each element of the domain maps to a unique element in the codomain. So any function that meets this particular requirement is also known as an injection. You can say it is an injection. You can also say it is an injective function. So they basically mean the same thing. So how do we describe it, using a statement? So this is the statement that, can be used, okay? So for all p in X, so in this case, because of this notation, we know X is the set, that we know as the domain. So every element in X and for every element in X, okay? So P and Q are both coming from X. Now the question is, can they be the same? Yeah, they can. Surely they can be the same. They can be different. They can be the same. So we are looking at every single possible way to pair up elements in X. Okay, so if X has, let's say, 1, 2, and 3, then we are asking what happens when P is 1 and Q is 1. What happens when P is 1 and Q is 2? What happens when P is 1 and Q is 3? What happens when P is 2 and Q is 1? What happens when P is 2, Q is 2? What happens when P is 2 and Q is 3, and so on. So that's basically generate all the possible ways to pair up values that we can find in X. So what is interesting about the following statement, which is this portion of the equation, is that it is an implication. In other words, if P and Q are the same, okay, when P equals to Q, the implication itself is true to begin with. Because by now, I hope that we already understand that one kind of tricky part about the implication is if the left-hand side, also known as the precedent, is false, then the implication is true. So the only time we really have to look at the right-hand side, which is known as the consequent, is when P does not equal to Q. So when P does not equal to Q, then we want to make sure that P and Q map to different things in the codomain. So when we use f of P and f of Q, we are looking at what elements P and Q are mapped to. So I just want to ask, are there any questions about this notation? This notation over here, this statement basically says, two different domain elements must map to two different elements in the codomain. Do we have any questions about that?
Could you give an example of that?
Okay, sure. So let's go ahead and look at an example. I'm typing off screen so you cannot see this part, but I hope this will pop up here. Okay, very good. All right, so we're gonna say examples related to injection. All right. All right, so the first thing is, we need to know that f is a function to begin with. In other words, if f is not a function, then we don't even bother to use injection, surjection, and bijection to describe it, because these terms only apply when we have a function. So the first thing I need to do is to establish what is the domain and what is the codomain. So I'm going to use this notation that you cannot see just yet, okay, but I will show it as soon as I'm done typing over here. Yeah, it's kind of interesting because in today's meeting, before the meeting, the professors were just talking about, how document cameras, basically, they were all sold out because everybody is teaching online, and a lot of people use document cameras because that's kind of a very intuitive way to teach a class interactively, is to use a document camera. I used the document cameras many years ago, and I did not like the experience because my hand is kind of big and it shows on the camera, and the refresh rate is also kind of slow. Okay.
Like one of those Elmo machines?
Yeah. The Elmo machines are very expensive, and
They're also horrible.
yes, they're very horrible especially for the money that you pay. They are not Linux friendly at all. In fact, most do not work with Linux. They require a Windows driver. But I got ones that are basically just a stand with a webcam on it, and the webcam has a reasonable resolution, that's basically what you just need, as a document camera. But the problem with a document camera is when I write over a piece of paper, my hand is actually really big, on the screen of you guys, right? So, that's kind of really distracting. Whereas, when I do something like this, yeah, you have a slight delay, but when you see it, you actually get to see the intended result. So I don't really use a document camera anymore. And then my PC is also a tablet capable PC. So I can just use my PC, and switch it into the tablet mode, and then I can just write on it. And you guys can see what I'm writing like right away, but without having to see my hand. So that's kind of the advantage. All right, so let's take a look at the definition of this f over here. So by using this particular notation and saying that yes, this is true, that means f is a function, and the domain is 1, 2 as a set, and then the codomain is AB as a set. Okay, so now the question is, then I'll give you some examples, okay, and you guys can tell me whether it is a surjection or not. Okay, so the first example, I'll put example 1, and obviously you cannot see it quite just yet. Okay, I'm gonna finish typing first. Okay. All right. So this is the first example. F is a set of 2 tuples, and for each 2 tuple, the first item comes from the domain, and the second item comes from the codomain. So in this case, what about this particular f? First of all, is it a function? If I know that 1, 2 is the domain and AB is the codomain, is this f in example 1 a function? Yep, okay, very good. Okay, so we all agree that this is in fact a function, because in order to qualify as a function, all we really need is every item or every element in the domain is mapped to one and only one thing in the codomain. And in this case, that requirement is met. So we can now say is a function, but we can also look at this and go, but is it an injection? Okay, is it an injective function? The answer is no. Very good. Okay, it is not an injection. It's not an injection because when you look at how the elements 1 and 2 from the domain map to the codomain, they map to exactly the same thing. In other words, different elements in the domain are not mapped to unique items in the codomain. So that makes this function not an injection. Okay, so let's go ahead and take a look at the second example. I'll call this example 2. And this is it. So this one is a function. So we'll change the statement here. It is an injection because when you look at the elements of the domain, okay, 1 is mapped to A, 2 is mapped to B. So for each element in the domain, they map to unique elements in the codomain. So we are good here, okay? This is indeed an injection. All right, so let's complicate things a little bit here. So what I'm doing here is I'm first redefining the mapping. So this time I'm looking at a different f, okay? So this particular f has a domain of 1, 2, and a codomain of A, B, and C, okay? So now we'll go ahead and I'll do some more copying and pasting. So this is example 3. And so we look at this function, we look at this particular definition here, where f is a set of 2 elements. The 2 elements are basically the same as what we had before over here. So 1 maps to A, 2 maps to B, but it is still an injection. An injection doesn't say anything about can we have leftover things in the codomain that nobody from the domain maps to. Injection doesn't say anything about it, okay? All injection is saying is every element in the domain has to map to a unique thing in the codomain. It doesn't say anything about, but can we have leftover items in the codomain? So it is perfectly okay in this case because, for each element in the domain 1 and 2, each one maps to a different thing in the codomain. So C not being mapped to by any element in the domain is not a problem. So are we good with injection? Is the example working?
Yeah, that's perfect.
All right, excellent. So now we can go back into the notes. So I'm just going to I will just move things around a little bit here so they're right next to each other. So the other thing to say exactly the same thing here, but using cardinality instead, is to say for each thing in the codomain, okay, you can have up to one thing from the domain to map to it. That's basically what this particular little statement is saying. So if you read it from here, for all Q in Y, okay, so that means by the time we get to this portion of the statement, we already know that Q is an element of the codomain. Now, in order to use this, we also have to be given that f is a function to begin with, because if f is not a function, then we don't even bother to try to figure out whether it's injective or not. So by the time we get to the set description, now we are saying, PQ as a two-tuple is in the set that we are concerned about if and only if PQ is an element of F, okay? So in this case, P is what we call a free, it's a free variable. It is not bound to a particular value, but Q is. So by the time we get to here, we already know that we are talking about a specific Q that is an element in the codomain. So that means, we are trying to find out what element in the domain, okay, because P is coming from the domain. So how many two tuples contain Q as the Q that we are talking about here, but the P can be anything as long as PQ is in the function F. So we want the cardinality of this particular set to be less than or equal to 1. It equals to 0 when no one is mapping to that particular element Q in F. In other words, if Q is bound to C in this particular case, then the cardinality of the set that we were talking about would have been 0, because nobody from the domain maps to element C in the codomain. On the other hand, it can also be 1, because when we look at in our example, if Q is B in the codomain, then the cardinality of the set that we are talking about would have been a 1 instead of a 0. And Omar is asking, you don't have to say that P is in the domain X. No, I do not have to say that, because Q is already known as a function, and if F is known as a function, then for every two-tuple in F, the first item in the two-tuple has to come from the domain. So that's why I don't have to mention that. And that assumption is done here. Let us assume the function of interest is F. So I already know that F is a function, and I also know that X is the domain and Y is the codomain. Okay, but good observation there, Omar. Because if I did not have this assumption, then I would have to be very specific and say that P has to come from X or the domain. So here we have an example, which is kind of the reverse of what we have, on the side. So so you can use this. I mean, we basically talk about the same thing already. It's just a matter of we use a different set in this case. So shall we move ahead to talk about surjection now that we have talked about injection? Okay, I don't see any. Okay, let's move ahead then. So surjection is, if you look at the definition in English, all it is saying is a surjection is a function where every element in the codomain is mapped to. Okay, that's it. So let's go ahead and figure out a few examples. And once again, okay, it's important to point this out. Once again, surjection, or the qualification of surjection, is an additional property on top of being a function. In other words, if F is not a function, we are not going to even talk about whether it is a surjection or not. So being a function is the first thing we need to confirm, and then we will look at an extra property whether everything is mapped to in the codomain. So so what I'll do is I'm going to give you some examples so we can kind of think through that a little bit. So here is examples related to surjection. And we'll go ahead and start with an F. And this time we'll use, we can use about the same thing. We can use 1, 2, and map it to, well, we'll map it to AB first. Okay, so we'll map it to AB, just like that. Okay, so it's kind of using the same setup as the first example, in injection. Okay, in fact, we are going to reuse exactly the same example, but this time we don't really care whether it is injection or not. This time we want to know whether it's a surjection or not. All right, so the first thing is we look at example 1. We know it is a function not only because I told you it is a function, but when you look at the actual definition of f as a set, okay, it qualifies as a function because every element in the domain is mapped to one and only one element in the codomain. So it's definitely a function. But we want to know whether it is a surjection or not, whether the function is surjective or not. So what do you guys think? It is no. Okay, very good. So the answer is no to this question, okay, but not surjective, okay? Because element B of the codomain is not mapped to. That is why this is not a surjective function, okay? All right, so let's look at a second example. All right, so the second example looks like this. This one is surjective, okay, because it is quite clear that both elements in the codomain are mapped to. It is also quite clear that f is a function to begin with, because we can see how each element of the domain is mapped to one and only one, and in this case it's also unique, but we don't care about uniqueness, okay? What makes this mapping surjective has to do with everything is used, okay? So I'm going to give you guys, some more interesting examples. Okay. So this would be another one. So this is an interesting one because, you would say, oh, this function serves no purpose because there's only one thing in the codomain, and if this is indeed a function, then everything has to map to A. So in order to avoid confusion, we'll just call this function H instead of function F. There we go. So now we want to know, whether it is surjective or not. Okay. Now in this case, there's no example 1 and example 2. There's only one example because there's only one way to create a function out of a domain of 1, 2 and a codomain of A. Okay, so there's only one way we can do this. So in this case, H equals 2. You cannot quite see it yet. When I finish typing, then you can see it. There we go. So this is the only way we can define a function out of the domain 1, 2 and the codomain of A, because there's not really any choice. So this one is a function and it is surjective. I mean, that kind of goes without saying, right? Because if you only have one element in the codomain and it is a function, then everything maps to that one and only one thing in the codomain. Does that make sense? I hope so. Okay. Are we good? All right, excellent. All right, so let me show you yet another example. So here we have function g, and the codomain is A, B, and C. Like so, okay? H is not injective, that is correct. H is not injective because both elements 1 and 2 from the domain, they map to the same thing in the codomain, and therefore it is not injective. Very good. So now we take a look at G. Okay, so in this particular notation, we only know that G is a function. It maps domain 1, 2 to codomain A, B, C. Okay, so you might say, well, that cannot be because the codomain cannot have more elements than the domain. No, it can have more elements than the domain, because remember, in order for G to be a function, the only requirement is every element in the domain is mapped to one and only one thing in the codomain. It doesn't say anything about do we have to use up everything in the codomain. It doesn't say anything like that, right? But this time we look at this and go like, well, let's think about, can we make G surjective? Is it even possible to make G surjective? So I want you guys to think about that a little bit, okay? Can G be surjective? All right, the answer is no. Joshua is correct. G cannot be surjective. So I'll answer my own question here, okay, with a no. So now the question is, because this is CISP440, so we focus also on how do we prove something. In other words, it's easy to find an example. Okay, if we look at f up here, and I say give me an example so that you can define f as a function, as a set of two tuples such that f is surjective. Okay, you can find one way to do it. In fact, there are two ways to make f surjective, because you can map 1 to A, 2 to B, but you can also map 1 to B, 2 to A. Both of those variations of the function are surjective. And if I ask, can you make f non-surjective? Well, that's pretty easy. Map 1 to both to A, or map 1 to both to B, and we're done. Okay, so and then when we look at H, okay, you can quite easily tell that, yep, we can make it surjective, because that's the only way to make it surjective. But now we look at G, the answer is no, we cannot make G surjective. And you guys already know why, right? Because the domain has 2 elements and the codomain has 3 elements. So there's no way to use up every element in the codomain. That sounds good as English statements. But now the question is, but can that be considered a rigorous proof? And the answer is no. Okay, because in a rigorous proof, all you can use are the symbols in mathematics. So as far as we are concerned, up to this point, we have introduced operators like element of, cardinality, how we can define a set, what I would call an ad hoc set, where we have curly braces and then we describe what elements go into the set. So unless you can express everything using those symbols and also logical operators like and or not, implications, and so on and so forth, it doesn't count as a rigorous proof. So now we haven't really talked about proof by contradiction, but to prove that you cannot define a surjective function using this domain and this particular codomain here, that requires the understanding and application of proof by contradiction. Now we will talk about proof by contradiction in this class. This is really just a preview of what we will talk about. That would be kind of handy. If we knew about proof by contradiction, then we would be able to prove why the answer is a definite no. I know it makes sense to all of you already, but can you prove it in rigorous math notation? That is the question. All right. So are there any questions at this point about injection versus surjection? Okay, no questions. Any specific question about G? The way G is described, it is a function, and 1, 2 is the domain, ABC is the codomain, and it cannot possibly be surjective. Okay.
So for a function to be surjective, the domain has to have enough values for the range.
Aha! Now that is a very good observation. So the observation is, okay, so let me use the note area here, okay. That is a very good observation. So in general, I'm just typing on the side so you can't see just yet. Okay, so we have FGHI is not a very good name for a function, is it? We have J, we have K. I suppose we can use K here. Okay, so I'm using K is a function that maps a set X to a set Y. Okay, there we go. Okay, so in general, if we're looking at a function, I just call this K here, and X is the domain and Y is the codomain. Let me see how I can. Okay, this is how I would say it. Okay, if you look at the cardinality of Y, if the cardinality of Y is greater than the cardinality of X, then we know that K cannot be surjective. There we go. All right, so I'm just reading the comments here. Sandip said, when you say that every element in the domain has to map to one, I didn't say only one, I said one and only one. So it has to map to one and only one element in the codomain. Does the mapping have to be unique? The answer is no. We talked about that last Thursday. That when I said one and only one, it does not imply uniqueness. And then Omar is saying, will we be doing proofs? Oh yeah, definitely in this class. All right. So any other questions? All right. All right, so let's get back to what we are talking about here. So in general, if I want to name a function, let's just call it K, X is the domain and Y is the codomain. If the cardinality of the codomain is greater than the cardinality of the domain, we know that K cannot be surjective. Now, if K cannot be surjective, does it mean that it has to be injection and injective? No. Does it have to be not injective? No. We just know that it cannot be surjective. This has nothing to do with whether it can be or cannot be injective. Now you can also say something like this about injection, but it goes kind of the opposite direction. So I'm going to go back to the previous one and paste something. So in the other case, if X as a domain has a cardinality that is greater than the cardinality of the codomain, then we know K cannot be injective. So this is what I'm just adding here. So in general, if you look at a function K, where X is the domain and Y is the codomain, if X has a if the cardinality of X is greater than the cardinality of Y, then we know that K cannot be injective. Kind of makes sense, right? Because in order for K to be injective, each element of X has to map to a unique element in Y. So that means for any injection, the cardinality of X has to be less than or equal to the cardinality of the codomain. And likewise, okay, when you look at something that is surjective, that means the cardinality of the codomain has to be less than or equal to the cardinality of the domain.
Is there any offshoot cases where this isn't the case?
Okay, when you say where this is not the case, can you clarify what this is referring to?
In general, it usually means that this will happen in most cases, but in some very extraneous cases, it won't be this case. So will it all
in general does not apply. There are exceptions.
Gotcha.
It simply means that this is this is the generalization.
Okay.
Yep. So I understand that, because in when we use the phrase in general, sometimes, but not all the time, it implies there are exceptions to the general rule, but in this case, it is universal. So to be much more specific, I'm going to use the quantifiers that we have been using in our class. So we'll just say that for all function k, there we go. So there are no exceptions to this rule. And the same thing over here for all function k. Come on, cannot type today. There we go. So that's a good point. Okay, I really kind of need to be careful when I use English words like that. Cool. So are there any questions regarding injection versus surjection? Okay. Let's go back to the module. The module, basically uses another way, to specify, what makes a function a surjection, and this is it. Okay. And when you look at these two descriptions, they are very much similar, right? This is for injection, and this one here is for surjection. The only difference is this is a greater than or equal to 1, whereas the other one is a less than or equal to 1. That's the only difference. So let's just kind of take a closer look again. This statement is saying, let's consider everything in y. Okay, so for each element of y, we evaluate whether this is true or not. That's basically what it's saying. And the entire statement is true if and only if everything that we described here is applicable to every element in y. Okay. All right, so we now, once we bind q to be an element of y, so now we look at, what is the criteria or criterion in this case. So the criterion in this case is the cardinality of a particular set has to be greater than or equal to 1. But what set are we talking about? What is in this particular set? A two-tuple PQ is in this set if and only if PQ is an element of the function that we are dealing with here, that we're trying to evaluate. So what it is really counting, okay, what the cardinality is really counting is counting how many things in a domain is mapping to this particular element Q that we're concerned about at this point. So if the number of items in a domain mapped to Q is greater than or equal to 1, and we can say this for every single element of the codomain, then the function is known as a surjection. So is that okay? Is everybody relating this description to what we otherwise intuitively know as everything in the codomain is mapped to? Because this is the other way to say it, but without using any English words. All right, so we got some example. We got a question from Omar. Is there a shorthand symbol to imply a variable like f or k is a function? I do not know of one. There may be one, but I just do not know of one. I know that when we use this notation, it is already, if we state this, that means f is a function and x is the domain and y is the codomain. So that's the only notation that I know of. I'm not aware of any other notation that just confirms that f is a function. Typically, if you want to confirm that f is a function, you also want to know what is the domain and what is the codomain, and hence this notation is handy. All right, so are we okay now with injection and surjection? All right.
Everything looks good.
All right, excellent. So now we can move on to bijection. Bijection is really easy because it just means something is both an injection and a surjection. Okay, so we can say it's a function that is both injective and surjective. So what we are doing, okay, is we're combining two statements. So when we look at this particular statement here, we're now combining this statement with this statement over here. So let me see if I can display both at the same time. I have to zoom out just a little bit. Come on. There we go. Okay, I don't have to zoom out actually. So if this has to be true and this has to be true, well, that's pretty easy, because this one is saying, blah, 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 the cardinality thing has to be less than or equal to 1. This one here is saying blah, blah, blah. The same blah, blah, blah has to be greater than or equal to 1. So we are now saying something has to be less than or equal to 1 and greater than or equal to 1 at the same time. What is the easier way to say it? It just has to be exactly 1, right? Yep, exactly. So Alex has got it right. So that's why, the qualification for a function to be a bijection, to be a bijective function, that's the other way to say it, is when you count how many things are mapped from the domain to a particular thing in the codomain, it has to be exactly 1. Okay? That's
Could you
it.
go to the whiteboard real quick?
What?
Did you go to the whiteboard really quickly?
Yes.
So in the case of where f is equaled to the set of a1 and 2b, that would be a function and a bijection. So yeah,
Yes.
example 2.
Yep.
So that would be a case of bijection, because
yes,
it's both this surjective and injective.
Exactly. Because it is, we already concluded that this set here is an injection, but we also concluded over here that it is a surjection. So that means it is both injection and surjection, and that means it is a bijection. Yep, that's exactly it. All right. Alrighty. So let me see, I got a PM. Okay, it's not related to this class, so I can get back to that later. Oh, I also got a message from the general channel. Oh, that's about prerequisite, co-requisite of CISP440. Okay, so I'm gonna answer that question later. All right, so getting back to today's text channel. Okay, so no additional questions. All right, so the idea, the whole discussion of injection and surjection is so that we can get to bijection. In other words, injection by itself is kind of interesting, has some interesting conclusions that we can draw, but it's like meh, not too exciting. Surjection is kind of the same way, it's kind of like, yeah, well, it's kind of interesting, but why do we need it? Well, we need those two in order to get to bijection. So bijection is actually what we really want to get to. So what is so special about bijection? The first thing about bijection is if a function is a bijection, then an inverse function exists for that function, okay, because it is a one-to-one correspondence. And that is our password or passphrase today for taking roll. So you might want to do that roll taking activity like right away. It is one-to-one literally, okay? Those are the digits, 1 to 1. In other words, type in 121 in base 10. Yep. Yeah, I have to specify it is in base 10 because the value of 121 can appear entirely differently depending on which base we are using. So I'll give you guys a little bit of time to type it in and just kind of confirm in the text channel when you're done with it. So when I see a few people confirming, then I have a pretty good idea that it is okay. So I'm not just gonna move on when one person does it, because I know some of you are very, very quick with doing web stuff. Okay, we got 4 people out of maybe 12 or so, and I know some people do not ever respond. Okay, very good. Okay, so I think it is a good time. In other words, if you cannot get it done yet, just kind of text in the text channel, let me know that you're not done. Okay, excellent. All right. So moving on to the concept of an inverse function. So in this case, a bijection is reversible. Now, reversible is always an interesting and useful thing, because now if f is an injection, then we know there's a companion to f called f inverse. Now, what is interesting about the f inverse is the domain is the other guy's codomain. The codomain is the other guy's domain. Okay, and this notation here, let's check out these two notations because I want you guys to get comfortable with reading quantified statements like this. So let's focus on the first one first. Okay, so we want to know what is E. So this is basically saying, this entire thing is true, but if and only if for every element E in the domain, well, I shouldn't say domain because it is confusing whose domain we are talking about. So we'll just say that for every element in X, okay, F inverse applied to F of E equals to E. Well, that's because that's exactly what inverse does, right? Because it reverses the operation. The other one is doing exactly the opposite. For every element in Y, if you first take the inverse function F to this E and then apply the function F to it, then you get E back. So I'm pretty sure most of you know this already because you have taken algebra 2 already, and many of you have taken calculus. So when you look at this is not really a good example, but I'm gonna use it anyway. Okay, so when you look at sine and arc sine, the inverse of sine, okay, that one is the function and the other one is the reverse of the function. But there's one little problem with sine and arc sine. Can anyone kind of, it depends on a few things, okay? But if you think about sine and sine, cosine, tangent, and stuff like that, there's a little bit of a problem. Okay, I'm gonna wait until Omar and Alex are done typing because I do want you guys to. Exactly. Yep. So they're both correct. Okay. Good job. Okay. Omar stated, that it is not injection if you use real numbers as the domain. Okay. So if you use real number as the domain, then it is not injection because the sign of 0 is 0. Okay. No big deal. But the sign of pi is also 0. The sign of 2 pi is also 0. The sign of 3 pi is also 0. So it is not injective, okay? But Alex is right as well, because Alex is saying, well, you can turn it into an injection, but you have to limit the domain to be to exclude sign and minus signs. I mean, pi and minus pi, okay? So it has to be the real number line, that goes from just a little bit more than pi to just a little bit less than pi. So within that domain, okay, you can still make it a bijection. Let me see. Yep, it will still be a bijection in that case. So they're both correct. So this is tricky, right? Because the tricky part is when by controlling or I'm trying to think of the right word in my head. By selecting your domain, okay, you can turn a function into bijection or not bijection. Certain things are like that. Okay. All right. So are we good with that? Are we good with this notation here? And are we good with, the example of using sine and go like, well, that's not really a very good example because we have to be very, very careful with, what we choose to use as the domain. So are we good?
Yep.
Okay, excellent. So this is also why, the prerequisite of, algebra 2 is really important, because otherwise I cannot assume that you guys already understand, what I just said. All right. So the proof of this is, okay, that's bad English, right? I mean, let's example what we know about a bijection. So let's use an example, okay? I don't know what I had in mind when I typed that sentence, which occurs quite often, unfortunately. Okay, so let's see what we know about a bijection. Because a bijection is a function, we know the following is true. So this is basically going back to how we define a function. So so Q is something that is in the codomain, and use this notation basically says everything in the domain is mapped to one and only one thing in the codomain. And the other one is down here. So we basically get to this part. This is what we saw earlier. Okay, this is the qualification of being a bijection. So when you combine these two, oops, sorry about that. So when you combine these two, it is basically saying the same thing here. So that's why we can look at it in a reverse way, because when you look at how we define okay, so maybe I should go step by step. Okay, let's take a look at this statement here. Doesn't this look familiar? This is what we know, this is how we define a bijection. So when we define a bijection and y is the quote-unquote codomain of function f, this is what we specify it. But when we use an implication. So the implication is basically just like this. For every element called PQ in F, it would exist as QP in F inverse as an inverse function. That kind of makes sense, right? Because if we are mapping P to Q in the original function, then the inverse function would just kind of flip it around and go like, okay, we're going to map Q to P, right? But so it kind of makes sense. But the other way to look at this is now we are saying, oh, but Q is coming from the domain from the perspective of the inverse function, and P is coming from the codomain from the perspective of F inverse. So when we look at it that way, that means F inverse is also a function because it meets the requirement of being a function. So that's really kind of the interesting part is when you start with a bijective function F and you flip the ordering of the two tuples inside each element in F, then you end up with F inverse. And the way we define that F inverse is automatically making it a function as well because it meets the requirement of being a function. So that's basically what this discussion is talking about. So when you have a bijective function, then the other way around is also definitely going to be a function. So are we okay with this discussion so far?
Yep.
Okay. All right. So that concludes that every bijection has a matching inverse function. If you know that f is a bijection, then we know there's an inverse function that has to exist.
Could you show us a short example of an inverse of one bijection?
Yep, absolutely. So let's go back to our whiteboard area. And what we'll do is we pick out one particular one. Okay, so we'll make a new point here. Example relate, maybe just one, so I would use singular for now. Related to bijection. Okay. And we're gonna reuse this portion and take out this one, change it a little bit like so. Okay. All right, so I'm just gonna put I'll put this much on the screen at this point. So we're basically just reusing what we know as example 2 of injection and also example 2 of surjection. It's the same, the same setup. So this one has an inverse function, okay, and the inverse function, which I would denote as f minus 1, superscript, okay. So I'm going to type this, step by step because I want you guys to be able to kind of look at it in a step-by-step way. And it doesn't seem to like that. Huh.
So, Tack, if a bijection if we go to the inverse of a bijection,
Uh-huh.
in a case of that, both x and y must be equal, correct? Because
Yeah.
if
Okay. Let's back up just a little bit. I don't want to cut you off, but I think it's important to to specify the cardinality.
okay,
Yep. The cardinality of x and y must be the same for any bijection. Is that okay?
yes,
Okay. Okay. Go ahead. Sorry, I did not mean to.
I was just clarifying that in order for the inverse of a bijection, the cardinality of x and y needed to be the same.
Yep. In order, if a function is a bijection, then the domain and the codomain have the same cardinality, which gets very interesting when we are dealing with domain and codomain that have infinite number of elements. But at this point, we just want to focus on this particular example, which is very, very, it's very countable, and we're enumerating everything, right? Because in this case, if I define f to be 1a, 2b, then the inverse function f inverse is going to be mapping a back to 1, b back to 2. But f inverse is also a function. When you look at just this portion here, hey, that's a function. Except the domain is AB and the codomain is 1, 2 in this case. So is that okay? That's really just a quick example, but it's reusing something that we have been talking about. All right. So now let's go back to the previous example, okay? The sorting example, okay? So let's go back and talk about, what is the description of a sorting algorithm. Okay, so I'll go back to the whiteboard area, okay, and we'll say, okay, so, let me see how I should describe this. Okay, we'll say predicate that has, okay, that's statement that has to be true to describe a sorting algorithm. Okay, so this is, we're getting back to the whole discussion of the idea of what is a set, what is a function, and so on. It really is language. Okay, you're basically learning a new language up to this point, just like learning Spanish, learning German, learning Japanese. You're learning a new language because we need to express certain things using this language, okay, that we call mathematics. Just in case you don't know, okay, different languages have different vocabulary to describe different things, okay, and part of it has to do with culture, part of it has to do with exposure to things, that are local to a certain community. So if you look at the Japanese vocabulary, they have one sensation, to describe the sensation of MSG. So, Chinese doesn't have that word. English doesn't have that word. We just say tastes like MSG. But in Japanese, they have one specific word to describe the sensation of MSG. So mathematics is kind of the same thing, okay? Obviously has nothing to do with MSG, but it has very specific vocabulary and also structure to describe things in a very concise and also precise way when it comes to logic. So that is kind of what we want to know is how do you describe a sorting algorithm? How do you describe if this is the input, the output has to be blah, 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 okay? So we'll go ahead and start with, I do not know. You can probably look it up. And Japanese word for MSG sensation. Taste. There we go. Taste.
Hey,
Yeah. umami, umami. Okay. Yep, there we go.
Isn't that also the word for the fish cakes?
Well, they might have the same pronunciation for multiple kanji. So kanji is borrowed from Chinese. So there can be multiple different kanjis that have the same pronunciation. So when you get to the pronunciation, it can be ambiguous. Like the word sake, that can be the wine, but it can also be raw salmon. But they're written entirely differently. It's just that they have the same pronunciation. All right, so getting back to the sorting algorithm. Okay, so we can now first describe initial conditions. Okay, so the initial condition is simply to say, okay, let's denote. Okay, this is just a notation, right? So all we want at this point is to say what are the initial values for each element in the array. Okay, so we'll first have to specify a few things. Okay, so we'll specify that A is the name of the array. Okay, and then the second thing we want to specify is how do we describe the initial value of each element in the array. So we'll say k underscore I equals to A bracket I is the initial value of each element in the array. There we go. And if you want this to use quantifiers, because I think it's good to learn how to use quantifiers in this context. In other words, what is the range of values for this I? Then we just add quantifiers here. We say for all I in the set, and this time I'm going to use the range, 0 dot dot bar a bar minus 1, and put a close parenthesis over here. That's a typo, that's why I didn't recognize it. There we go. So let's go back and take a look at this here. Okay, so this is not a derivation, it is actually more as a given. So we are basically saying, if you consider every value I that is between 0 and bar a bar, okay, let me put in the close parenthesis. Oh, okay, we do have the close brace. So for each I being a valid index, we are defining k of I to be the initial value of A bracket I. So this way we can refer to the initial value of each element as the input condition of the array. Okay, so now we want to specify what about after the sorting algorithm. Okay, after running an algorithm, this is what we want. Okay, so there are several things that we want. Okay, the first one is we want the ordering in the array after it is sorted. Okay, so to specify that, this is something that we have seen already. Okay, so it's not new, but I'm just gonna rewrite it anyway. So we have for all again. So for all I in, so this time the set is going to go from 0 to bar a bar minus 2, because in order to specify the relationship between elements, we only have to specify the index from the first one to the not the last one, but the second to the last one. Because the way we specify ordering is to specify A bracket I has to be less than or equal to A bracket I plus 1. And I need a close parenthesis over here. There we go. Oh, I'm missing a close square bracket. There we go. All right. So this part here, okay, for all I from 0 to bar a bar minus 2, we're looking at all the valid indexes except for the last element. Okay, so we're going from the first to the second to the last element. And then we say, each element in array A has to be less than or equal to the next one. Okay, and we are looking at an algorithm to sort it in a non-decreasing order. So less than or equal to is what we want, and not just less than. So is that okay so far? But this requirement is easy to meet because all you have to do is to reinitialize the array and just initialize everything to 0. Okay, it will automatically meet this requirement. So that's not enough to specify what we want to specify. So the second thing we also want to specify is have f as a bijection, or we know it as a bijection. Okay, and we also want to describe f a little bit better. In other words, we want to specify what is the range, what is the domain and what is the codomain. So they're basically the same. The domain and the codomain are both the same. They are valid indexes into the array. So we go from 0 to bar a bar minus 1 to the same set. In other words, the domain and the codomain are the same because they're both just trying to describe all the valid indexes, just like that. Okay, so but this time we don't just describe f as a function. We now describe f as a bijection. In other words, there's an inverse function, for there's an inverse f inverse in this case. Okay. So now we also want to describe. So this is the most difficult one to describe. The one that we kind of missed, describing previously, is every element in A after the sorting algorithm has to map to the initial value of a unique element before it is sorted. So this way, if you are given an array of say 0, 1, 1, you cannot have 0, 0, 1 after sorting and call it be good, even though 0 and 1 are both still present in the sorted array, but the count has to be correct. Okay, so the way we describe that is like this. Okay, so we now say for all I in the set of all valid indexes 0 to bar a bar minus 1. Okay, so now we want to describe something in the middle, between the parentheses. So now we have to say a bracket I has to equal to, this is after running the algorithm, so this is the final value of an element in a particular element in the array. So now we have to say that it has to match k subscript f of I. You cannot see it yet because I'm still typing it. There we go. So this is the last requirement that is kind of really tricky, because now we are basically describing and say that each element in the array after we run the sorting algorithm, it has to equal to the initial value of an element in the array. But not only that, because if that is just a requirement, it's easy, right? We take the first element of the entire array and just copy it throughout the entire array, and it will still meet the first and the last requirement. But because f is a bijection, so that means each I has a unique f of I corresponding to it. So that means we are now making sure that every element in the array after sorting is matching a particular element, a unique element, before the array is sorted. Now you might ask, but what if we have two elements in the array that have the same value? Well, then you have your selection of f. Okay, you have different ways of describing f, but either case, okay, no matter which one you choose, that f has to be bijective. Okay, so it's better to show you an actual examples. Okay, so we'll go ahead and look at an example. Okay, so here is an example of the sorting. Okay, so the example of the sorting, okay, the array has the following elements. We'll say 0, 0, 1, 2. Okay. Excuse me, I'm going to turn off my phone here. All right. So let's say array A has initially has elements. Let's make these out of order. Okay, so that makes it a little bit more fun. Okay, put the 2 here, put the 0 over here, and it's not updating. There we go. Okay. So what this means in this case is if I want to use the K notation, so in this case, what is bar A bar? The bar notation, when I apply that to an array, it means how many elements we have in the array. So bar A bar in this case is 4 because we have 4 elements in array A. And then we can now specify all the constants K, right? So we know K0 has a value of 0, K1 has a value of 2, K2 has a value of 1, and then K3 has a value of 0. Is that okay? It's just a notation, okay? Because the purpose of K is to denote, okay, what are the initial values in the array. All right. So now we also know, what the array is supposed to look like when it is sorted. Okay, array after sorting, it's going to be 0, 0, 1, 2. We know that, right? I mean, that's how you know about sorting. But now the question is, what is the function? Okay, what is a function f that can describe this? Okay, so we'll go ahead and take a quick look. So one possibility, okay, one possible f is like this. Okay, so we'll describe f as a set. We look at the initial, we map 0 to 0, okay, because that 0, at the very beginning, that can stay put. We don't have to move it around. What used to be in element 1 is going to be the last one. So 1 is mapping to 3 because this 2 needs to go here. So the index of the 2 has changed from 1 to 3. And then we look at the 1. Okay, so it used to be index 2, but now it is index 1. In other words, we're looking at this one over here, which has index 2 to begin with. And after sorting, it has, it still has index 2. Okay, I stand corrected. Sorry about that. So it doesn't move. Okay, this is a very good example because one of them actually does not move. And then when we look at the last one, which is the 0, this one did move. This is index 3 went before sorting, but after sorting, that 0 got here. So after sorting, what used to be in index 3, goes to index 0. So when I want to describe one possibility of this f, which has to be a bijection, this is one way to describe it. Now, let's double check a few things, okay? Because the first thing we want to do is to say, is f indeed a function? Well, if f is supposed to have a domain and a codomain, they're both the same, and they are the valid indexes into the array. So we look at 0, 1, 2, 3. Yep, those are all the valid indexes. Does each element in the domain map to one and only one element in the codomain? Yes. Okay, so it meets both of those requirements. Third requirement, we also want f to be a bijection. In other words, we want it to be injective and also surjective at the same time. So now we check whether it is injective. In other words, does it map everything in the domain to a unique element in the codomain? 0 got mapped to 0, so 0 in the codomain is used. 1 is mapped to 3, so 3 is now used. 2 is mapped to 2, okay, so we only got 1 left. So 3 is now mapped to 1. So it does meet the requirement of being injective. Now we want to see if f is surjective. In other words, in the codomain, we have 0, 1, 2, and 3. Are they all used up? Okay, here's something mapped to 0, something mapped to 3, something mapped to 2, something mapped to 1. So yes, all 4 elements in the codomain are mapped to. So that makes f both injective and surjective, which means it is bijective. Okay. But the next question is, but Tech, why did you use the phrase one possible, okay, instead of f has to be like this? Because there's another way to describe this f. Because we have two elements being exactly the same, okay? Here's a 0, here's another 0. So I have an alternative way to describe this f, okay? And it still meets the requirement of this is sorted. I mean, this meets the requirement of a sorting algorithm. So I'll say the other possible f is we just change the two zeros. In other words, we basically say this 0 is actually moved to here. So we are mapping 0 to 1, and then we say this 0 is moved over here. Oops, is moved to here. So we are now changing 3 to map to 0. So the other possible f is, it looks like this. Now, does it meet all the requirements? You know, is it both injective and surjective? Is it a function to begin with? Yep, it meets all the same requirement, but there are two possible f's to describe that will both meet the requirement that we want. So is that okay so far? Does everybody kind of relate, you know, why a bijective function is useful? What if f is not bijective? If f is not bijective, then we may not have a valid sorting algorithm. Is that okay? So now the question is, when was the last time that Iraj or Dave, you know, or Ryan describe a homework assignment using descriptions like this? Probably never, right? You know, I have never taken their classes, and I don't, you know, snoop around and ask, you know, my students to show me what their assignments look like from another class. But I'm guessing that they don't really use mathematical notations like this. They instead rely on the assumption that you understand what sorting is all about. Is that correct? Okay. So what is the point? Tech, you're teaching something that is totally useless because, you know, other professors, none of the other professors use, you know, mathematical notations like this to describe, you know, what qualifies as a sorting algorithm. So what is the whole point of doing this? What do you think? What do you guys think is the whole point of doing this? Go ahead.
Because you have the doctorate.
Well, Kakashan also has a doctorate, but I'm pretty sure that she does not teach CISP430 in this particular way or in any other classes. Well, this has to do with something that is actually practical, because most people are looking at this and go like, this is a lot of mumbo jumbo to say something that I already understand. Okay, you know, why do we have to go through all this trouble to describe what is the proper result of sorting? Okay. All right, so what I want to direct you is to do a little Google search. Okay, it's called automated theorem proving. Okay, that's one way, you know, that's one search that can find you something like that. So automated theorem proving, also known as ATP or automated deduction, is a subfield of automated reasoning. Some people call it AI, some people do not qualify as AI. But basically, it's just an algorithm, okay? It's a computer algorithm that is designed to prove theorems, okay? So you might now ask, okay, what is the purpose of, you know, proving theorems using a computer? Other than I can now go to Mathematica or Wolfram Alpha, you know, get some calculus homework done, copy and paste into the answer, and call it a day, okay? So besides that, okay, what is the purpose? What is the value of automated theorem proving? What do you guys think?
We can check if someone creates a new theorem, they can check if it's correct or not, instead of having thousands of peer reviews done and disprove.
Okay, so that's always good. But how does it apply in computer science? Okay, I can understand, you know, in the field of mathematics, Okay, they really want to make sure that theorems are proven correctly. But what about in computer science? What type of theorems are we talking about? And how do we derive those theorems? What is given to us? And what are the theorems, and why is it relevant to us? Okay, so what I'll do is I'm gonna switch back to the whiteboard first. Okay, so let's see if we can look at things this way. Okay, look at a program as a description of steps of operation. Okay, well, that kind of goes without saying. We already know that. All right, so Omar wrote on the text channel that we can prove that you cannot write a sorting algorithm faster than the time complexity, which we haven't really talked about yet, of n log n. So that is correct, okay? But this has to do with something different compared to time complexity. Okay, so when we look at the program as descriptions of steps of operations, then the first thing we want to do is to say, given a particular step and a precondition of that step, can we derive a post condition mathematically? There we go. All right, so I'm just kind of typing what I said. So given a particular step and a precondition of that step, can we derive a post condition mathematically? Well, the answer is for most cases, yes. Okay, so let's consider something like this. Okay, I'll just give you a quick example. X gets x plus 1. So this is the operation that this is the operation of concern. Okay, I want to know what this is actually doing. Now, I do not use the equal sign here, because if I used the equal sign, and this is in a mathematics context, x equals to x plus 1 is a stupid question, isn't it? Because x equals to x plus 1 has a very easy, trivial, and stupid answer. False. So I have to be careful not to use the equality symbol, and instead I use the left arrow to indicate this is an assignment operation. It is not telling me something is true or false. This is telling me that I'm updating variable x using the value of x plus 1. Okay, so, and I'm gonna use a precondition. Okay, so let's say the precondition is as follows. Okay, so there are two things that I know. Okay, the first thing I know is x is less than y, and the second thing I know is z equals to 10. Okay, all right, so this is my precondition. Don't ask me how I got to the precondition, I just know. Okay, so right before I execute the statement x gets x plus 1, this is what is guaranteed, okay, at that point. So now the question is, can I mathematically or logically derive or deduce a post condition? Okay, and also express it in a mathematical way. Well, let's take a look at this. Okay, we are changing x, but we are changing x in a reversible way. Now, this is why bijections are really useful, because it is reversible. So this means if I know that before the operation x is less than y, then we can also say something about, well, after the operation, we know that x minus 1 is less than y. Does that make sense? That's one thing that we know for sure, because the whole operation is to say, okay, the value of x is now increased by 1. But if I say, well, after it is increased by 1 and I take 1 away, that would still be less than y. Does that make sense? Maybe. I know we are running out of time, but I still want to get through this. And z equals to 10 is still the same, because the operation does not change x. Excuse me, the operation does not affect z at all. Is that okay? So given a precondition, which is this part here, given the operation that I'm interested in, and I can derive a post condition like this. Does that make sense? This is just a very quick example, by the way. So we can do the same thing with conditional statements. We can do the same thing with loops. We can do the same thing, we can now say, okay, now that the post condition of this statement is this, but that is really the precondition of somebody else. In other words, I can chain this type of reasoning from the beginning of an algorithm all the way till the end of the algorithm. So that means if I start the description of an algorithm like this, okay, and I go step by step using a method like this, then I'll get to a post condition, but not of one particular statement, but of the entire algorithm. And it's going to look like a mathematical equation of some sort. Okay, it's a mathematical description of what is guaranteed to be true when an algorithm is done executing. Is everybody still following me, even though we are kind of out of time, already out by 3 minutes? But I think it's important to establish the context just so that you guys understand why I talk about this and what you can do with it, okay, when you're out, when you're looking for a job, okay, what can you do with what you have learned in college? Okay, so the post condition of an entire algorithm is basically just one gigantic conditional statement, well, I should say a statement, okay, that is guaranteed to be true, okay? So now we want to see if that statement meets all of these requirements after a sorting algorithm. Because if we can prove that a post condition of a sorting algorithm is going to match what is needed, then we don't even need to throw any test cases at the program, because we have just mathematically proved that the algorithm is guaranteed to work for all cases. Isn't that, well, would you consider that useful? I certainly hope so, okay? Because let me show you what happens when we do not do something like that, okay? So this one didn't happen recently, but it is still a very good example of what happens. So you look up Heartbleed, and you go to the first link. I guarantee you this is not a questionable website. It describes what is the Heartbleed bug. Okay, now this happened in let's see, what is the time frame? 2014. Okay, so this happened like 6 years ago, but it has to do with programs not getting verified. Okay, and that's how exploits can happen, because programs are not accounting for certain input conditions, and as a result it would do something that the programmer did not originally anticipate, and in certain cases the program just crashed, and in other cases like this one, you can leak out really crucial information in a crypto communication engine. Okay, so that's basically what happens. So now what you also want to do, I hope some of you will do this, is to look up automated program verification and combine it with computer security. So the first one is from Wikipedia, which is great. The second one is from Springer.com. Okay, so if you click on the first one, which is Wikipedia, it will give you, okay, program verification is the process of applying formal methods directly to verification of code, which is theorem proving. Okay, they just use different words. Okay, verification of code is proving a theorem. So when we have methods to prove theorems automatically, and we can describe, let me go back to here, and we can mathematically describe what is the desirable outcome of an algorithm, then we have a way to prove once and for all that a particular algorithm is going to get a particular job done. Now that is big.
So it's like whenever you create a function that checks another function, kind of. So you give one function a set of values, and then you tell it if it's equal to another set of values or not.
That is using a specific test case. So theorem proving or program verification in this sense is not throwing test cases at a program. It is actually analytically going through a program and prove once and for all conclusively that the program will get the job done no matter what you throw at the program, as long as the input meets a particular requirement.
Yeah, I guess that's a normal Palooza.
Is that okay?
It makes sense.
Yeah, but it's a really important field because people are already starting to apply this to at least the most crucial parts of crypto engines and other crucial parts of an operating system. It's already being used. Now the problem with this, we'll see this in some later weeks of this semester. So the problem with automated theorem proving is it's not really easy. Okay, it consumes a lot of processing resources. So we can only do this to like shorter chunks of code. But if that shorter chunk of code is really the most crucial part of an operating system, like for security, how to encrypt the hard drive, how to encrypt communication, decrypting, and so on and so forth, then at least we're securing that part of an operating system. Now, does it mean that when you install a new driver in Windows, it won't crash your entire system and give you the blue screen of death? No, that probably will still happen. But you can at least test really crucial portions of your browser to make sure that your online banking data cannot be leaked by cross-site scripting to somebody else, to another web page. So that is the kind of thing that we are looking into, and this is really a field that was hot in the 80s. Between the 80s and the 70s, it was really hot. People started to talk about this, and they talk about all the possibilities. But the computers back in those times are very slow by today's standard, and as a result, they ran out of processing power, and then they said, okay, this is great on paper, we would love to do this, but practically we do not have processing resources to do all of this. And by the way, during that time, there's no such thing as the internet. The internet is something that came into existence in the 80s, right? So without the internet, you're looking at PCs, getting infected by floppy disks, right? So how fast can you spread a virus, and by floppy disks? Not very fast, okay? So it means, what wasn't practical, what wasn't doable in the past is now doable. And not only that, we have reasons to do it now. So that's why there's there's an interest in formal verification now, because we got the processing power, but we also got the risks, we got the exposure now that this becomes something that a lot of companies want to do. So I just want to point this out, to relate what we are learning to what industry is actually doing now, just so that you guys know the context of many topics that we are talking about in this class. All right, so we got Aaron and Omar typing. I haven't looked it up yet. The Morris worm. So a worm is different from a virus in the sense that a virus needs to be invited. So it has to be somebody clicking a link to get it installed. And the worm is automated. It just knows the security holes of a particular system, and it can spread itself. It is an active agent that can spread without any user interaction. A virus typically requires a particular interaction from a user, clicking a link, opening an email, clicking on an image, or something like that. Stuxnet is interesting. Okay, Stuxnet. Okay. Okay, there's a pronounces exactly the same way. So Stuxnet is interesting. because it is a very targeted malicious software. It is both a virus and also a worm. Okay, it is. You can look at this as a worm that is packaged inside a virus. No, the Stuxnet was intended to stop uranium refinement of certain Iranian nuclear plants, and it was done in a very, very professional way. It wasn't designed to get ransom, to make money. It was designed specifically to shut down a nuclear refinement facility in a way that it does not raise suspicion. Meltdown is also interesting because Meltdown is not just a software thing, it is actually a hardware software thing. So when you look at Meltdown as a inspector, they have to do with the hardware caching mechanism of computers. Basically, somebody, some hacker found what we call a race condition in terms of the caching hardware inside processors. So they were able to exploit that to get to data or memory content that a program is not supposed to get to. Now, I haven't really studied the actual low-level stuff, of Meltdown and Spectre, but I know that these two are not entirely software issues. They are basically a combination of software and hardware. So when they were discovered, the risk actually applies to Windows, Linux, and also Mac OS X, just about anything. Or one of them actually applies to everything. Yep. Well, hackers are, they're pretty much, people who think out of the box. Can they be mitigated using the same technique as software? Yes. So Meltdown and Spectre, they can both be mitigated in software, but I think in the process of doing that, you lose performance because you have to basically make sure of steps of things occurring in a particular sequence, because that's the whole idea of a race condition is, depending on several conditions, sometimes this gets to the finish line first and sometimes that gets to the finish line first. So in order to make sure that only A gets to the finish line first, B cannot get to the finish line first, it taxes the execution time a little bit. Yep, some of the patches. Yep, exactly. There's no way to, if you are not changing the processor, I don't think any fix to Meltdown or Spectre would not impact performance. Now, the proper solution is to fix it in hardware. So I think the newer processor coming out would probably have that particular problem solved. But that's just my guess. I have not been following up on Meltdown and Spectre. Oh, by the way, for the rest of the class, if you need to go on and do something else, like have lunch, go ahead. We are definitely doing something out of topic now, out of scope of the class. All right, cool. Okay, but it is kind of good to establish this context just so that you guys know why math is really important when it comes to security. And security is important everywhere, right? Even in League of Legends, it is still important to make sure that people cannot run bots. So that's computer security right there. You mean my mother tongue? Okay, because I'm not sure whether you're asking about my primary programming language or my primary, actual natural language. It's Cantonese. Yeah, well, it is what it is. All right. So I'm gonna stop the streaming because it looks like we're done with all the topics today. But I'll still be on the text channel because it's my office hour.